The last time we talked, we discussed finding area within polar regions. So today we're just going to find arc length and slopes. So if you were in all of these, we're in the XY coordinate plane. So slope is the rate of change of y with respect to x. Slope is slope in all three, whether it be rectangular, parametric, or polar. Slope is still dy dx. A little later we'll discuss what dr d theta means, maybe not until the next talk. But dy dx is slope. And when we did it in parametric, we used the chain rule and we found out that dy dx is dy dt over dx dt. Well, we're going to do the same thing, except instead of dt now, we're going to use d theta. So we're going to say dy d theta over dx d theta. It just comes straight from the chain rule. Dy d theta is dy dx times dx d theta. The trouble here is that we have to deal with these relationships between x and theta and y and theta. These are pretty important relationships. We have to remember that r is not a constant. We're in polar. So these polar curves are going to be, r is a function of theta. So when we take dy d theta, when we take this derivative, we have to use the product rule. So we go the first function r times the derivative of the sine of theta plus the sine of theta times the derivative of r, which is dr d theta or r prime. Now we do the same thing for x. So dx d theta, we do the product rule. The first times the derivative of the second. Then plus cosine times the derivative of r. And that's it. That's the formula for slope. And if you want, you can just memorize that. I'm not very good at memorizing. So after all these years I've been teaching, I still don't have that formula memorized. If I ever have to find the slope in polar, it doesn't take but a minute to do what we just did. So that's kind of your choice. So let's go right into some examples. So we've got r equals the sine of theta, and we want to find the slope at the points on the curve. So what are we going to do? We're going to find dy dx, and we're going to use this formula. So r is the sine of theta times the cosine of theta plus r prime. Well, dr d theta, r prime is the cosine of theta times the sine of theta. In the denominator, we have minus r, so minus the sine of theta times the sine of theta. Well, that's sine squared theta plus r prime, which is the cosine of theta times the cosine of theta, or cosine squared. So you could just go with that, but if you're going to have to do this at many values of theta, we can try to simplify. Well, if we remember our trig identities, this is 2 sine theta cosine theta, which is the sine of 2 theta, and this is cosine squared minus sine squared, which is the cosine of 2 theta. So altogether, we can reduce this to just the tangent of 2 theta. And all you have to do is plug in values, and you can get the slopes on this curve. Well, if you remember, we've done the sine of theta. When theta is 0, you get r is 0. When theta is pi over 2, you get r is 1. And when theta is pi, you get back to 0. And we have the circle. So, what are some angles that we could do? Well, there's the angle 0. You get 0, 0. And the slope is the tangent of 0, which is 0, which makes sense. How about if we went to pi over 8 That's not a very big angle. That would be something like that. And that would be the point on the curve. What would be the slope? The tangent of pi over 4, or 1. So you'd have a slope of 1. That looks about right. Now, if you went to pi over 4, that's pi over 4. We're right at that point on the curve, and you get the tangent of pi over 2. Well, the tangent of pi over 2 is undefined, but it's going to infinity. So you would have an infinite slope there, which looks about right. Let's do one more. What if you went to 3 pi over 8, which is halfway between pi over 4 and pi over 2? So it'd be right about here. And then you'd have the tangent of 3 pi over 4, which is a negative 1. And that looks about right. So I'm getting some confidence in this formula that we derived. Let's try one on a curve that we don't know. Well, the two things we need here are r and r prime. So r prime is 2 cosine of theta minus a minus the sine of theta. So we only have to do it at one angle this time, so we can just figure out what r is at pi over 2. It's 2 sine of pi over 2 minus the cosine of pi over 2. So r is 2, and r prime is 2 cosine of pi over 2 plus the sine of pi over 2 is 1. So now we can just use those and plug it in to the formula. Well, we're plugging in pi over 2, so the cosine of pi over 2 is 0. R prime is 1, and the sine of pi over 2 is 1. Minus r times the sine of pi over 2 is 1, plus the cosine of theta is going to be 0 again. So altogether, the slope at that point is going to be negative 1/2. So really, slope in polar is not that hard to do once you know the formula. And the formula isn't too hard to derive if you understand how it's being driven. Okay, so just to take a little break, and this is how math teachers take break, let's do an area problem. Do a little review of what we did in the last talk, because area is so important in polar. So r equals 1. Remember, a picture is pretty important here. So r equals 1, we want to try to be kind of accurate if we can. And then r equals 2 cosine of theta. I think we've started to do enough of these. When you just have sine of theta or just have cosine of theta, they turn out to be circles. So when theta is 0, you get 2. Pi over 2, you get 0. And pi, which heads out in this direction, you get a negative 2, so that takes you back to this point here. So we get another circle that looks like that. And I think you remember that these places where they intersect are important. And I like to draw rays coming out of there. And where do they intersect? Because we're going to need to know that. We set 2 cosine of theta equal to 1. We get the cosine of theta equals 1/2. Theta is going to be negative pi over 3. Remember, we don't want to make it 5 pi over 3. We want to make it negative pi over 3, so we can go from a smaller to a larger. And the area we're looking for is inside the red circle and outside the black circle. So we're looking for this area right in there. So it's important to draw in your slice of pi. So we're looking for that part of this slice of pie. Well, you have to take the whole slice of pie, which is to the red circle, and subtract the black circle. So you can do it with two separate integrals, but since they all are using the same angles and the same formula, you can do it all in one. You can go 1/2 the integral of r squared d theta minus r squared d theta, but you can do it with big R squared minus little r squared d theta. And you can go from negative pi over 3 to pi over 3, because that's where you find slices of pi. They start here and they go up to here. And if you have to do this without a calculator, you might really be confident that this is symmetrical and just go from 0 to pi over 3 and double it. If you're not, just go from negative pi over 3 to pi over 3. So what's the big radius? Goes out to the red, so that's 2 cosine of theta, and the little radius just goes to the black, so that's just 1. Okay, so we're not practicing taking antiderivatives and definite integrals now, so I'm just going to leave that, but show you the other way you would do this. The other way to do it is to take this whole red circle, which is pi times the radius squared, and then you have to subtract out, and this is a little hard to see, but you're going to have to subtract out this football right in here from that circle. And if you look really closely, the football is broken up into 2 parts. Right up here, up to this green line right here, the slices of pi right here would only go to the black circle. Then, between this green line and the red circle, the slices of pi would just go to the red. So you have to split this up from 0 to pi over 3 for the red. So that would be 1/2 the integral from 0 to pi over 3, but then we're going to double it because we're only going from here up. We're looking at the symmetry again. And now we're just looking at this part of the football up until the green line. So that just goes to the black circle. So then it would be r squared d theta. And then you also have to subtract out 2 times 1/2. But now you're going from pi over 3 down to pi over 2. That's where you stopped tracing out that part of the circle at pi over 2. And now the radius of this one is the red. So you have 2 cosine of theta. Both of these should give you the same answer, and you should understand how to do both formulations. Okay, so now that we've taken a break, we'll go over and do arc length. And I think this late in the year, we should look at all 3 ways of getting arc length. Review rectangular and parametric really quickly. So basically, to find arc length, and I did this in a little more detailed way the first time we did it, but basically if we're going from, say, this point to this point, you're going to break this up into little sections and call this little section ds, and then we're just going to get the total length, we're just going to add those all up. And what adds up all those little ds's is your integral. So in all 3 forms, that's the way I'm going to get arc length. I'm going to add up all those little ds's. The only problem is it's hard to know where to go from along this curve. Everything is kind of in terms of x and y. So we have to look at dx. There's ds right there. This is dx, and this is dy. So if we use Pythagorean's theorem, knowing that we're going to make these ds's incredibly small so that you won't worry that this straight line is not the same thing as the curve, we can say ds is the square root of dx squared plus dy squared by Pythagorean's theorem. So in rectangular, you're going to take and add up all these ds's. So you have dx squared plus dy squared. And you're going to go from one x value, x equals a, to x equals b. But to have an integral, you've got to have a dx over there. So what we do is add a dx. But then we can't just do that unless we divide by dx. And we can do that inside the radical like that. So what do we end up with? The integral from x equals a to x equals b of the square root of, this becomes 1 plus dy dx squared dx. So we haven't used that formula in quite a while. Now, the only difference when we go to parametric, we don't want dx here, we want dt here. So we just do dt. And what do we get in parametric? The square root of dx dt squared plus dy dt squared. And then dt. And that would be from t equals t1 to t equals t2. We've done that one not too long ago. So, what do we do in polar? We're still going to do the same thing. The problem is, we have to go back again to use this relationship. It's not a huge problem, but it makes it a little bit harder. X equals r cosine of theta, and y equals r sine of theta. So let's see. How do I get the differential of x? Well, I've got a product rule. So I go r times the differential of the cosine of theta, which is minus the sine of theta d theta, plus the cosine of theta times the differential of r, which is dr. And I can do the same thing with dy. We go r times the sine of theta d theta plus the sine of theta times dr. But I really need dx squared. So to get dx squared, I have to square it. And the same thing for dy squared. So let's see what I get when I get dx squared. The first term would be r squared sine squared theta d theta squared. Then you get plus 2 r sine of theta cosine theta d theta dr. And then I get plus cosine squared theta dr squared. Let's do the same thing with this one. I get r squared sine squared theta d theta squared. Let's see, am I doing these? I want to make sure that we're doing these right. Okay, then this should really be, let's see, r times, that should be the cosine of theta. I could see something wasn't quite right. So this is cosine squared theta, d theta squared, plus, and now I get, let's see, r squared cosine squared theta d theta squared plus 2r cosine theta sine of theta d theta dr, and then plus sine squared of theta dr squared. And one other little mistake, that was supposed to be a minus because I missed that little minus sign right up there. So now we have to add dx squared plus dy squared. The good part is, if you look in the middle here, these are exactly the same, and this is plus and this is minus. So those two cancel out. And if we add these two together, they both have r squared and d theta squared. So we can take r squared d theta squared times sine squared plus cosine squared. And then on this one, we can factor out a dr squared times sine squared plus cosine squared. And this is such a nice identity. Sine squared plus cosine squared is 1. So now we have the square root of dx squared plus dy squared is the square root of this. So we can just get, for our length, the square root of r squared d theta squared plus dr squared. But we really want a d theta over here so that we can integrate. So we divide by d theta squared underneath the radical. And these cancel out, and we've got our final formula. It's the integral of r squared plus dr d theta squared d theta. And you're going to go from theta equals alpha to theta equals beta. So we've now derived rectangular, parametric, and now polar arc length. And don't worry, this is complicated. I made a couple little mistakes in there. You're not going to have to be able to do that. You're just going to have to know this formula. Okay, so let's try it on a couple of examples. Find the length of this curve. Well, this curve in general is kind of a cool curve. We don't have room to really plot it. But when theta is 0, you get the square root of 2. Say it's the square root of 2. And then what happens is, you can see as theta gets bigger, e to the theta gets quite a bit bigger. So the radii start out at the square root of 2, but they keep getting bigger as theta gets bigger. So it starts spiraling out, and it keeps going up, and it's going to keep going around in a circle, and the radius gets bigger and bigger and bigger. But we're only going to the natural log of 5. So we're not going all that far, and we're finding the length of the arc from here to here. So what are we going to do? We're going to use that new formula. What do we need? We need r, and we need dr d theta. Well, dr d theta is the same thing as r. The derivative of e to the theta is e to the theta. So the length is going to be the integral from 0 to the natural log of 5, the square root of r squared, which is 2e to the 2 theta, plus the same thing again, d theta. So altogether, you have the square root of 4e to the 2 theta. And the square root of 4 is 2, and the square root of e to the 2 theta is e to the theta. So it's a pretty easy antiderivative to take. It's 2e to the theta, and you're going from 0 to the natural log of 5. You can just take the 2 out front, and e to the natural log of 5 is 5, and e to the 0 is 1. So the total length of this arc is going to be 8 units. So I'm not sure that I went quite far enough, but right there is the square root of 2. So that's about 1.4 units from here to here. So this total length would be quite a bit longer than that. Okay, so let's end it with this circle. We graphed circles like this before. So when theta is 0, you get 2a. When theta is pi over 2, you get 0. And when theta is pi, you get negative 2a, which shoots you back this direction. So what we do is we have, again, this circle. And it has a radius of a. So, the formula says the length, and this is where it's important to know, that we didn't go from 0 to 2 pi. We traced this out from 0 to pi, the square root of r squared. So 4a squared cosine squared theta plus, now we have to go dr d theta squared. So dr d theta is minus 2a sine of theta. So when we square that, we get 4a squared sine squared of theta. So altogether, we have the square root of 4a squared times sine squared plus cosine squared, which is, again, I guess I should write it in there, just so I can cancel it. Feels good to just make that 1. And as long as a is positive, let's just say a is greater than 0 in this problem, the square root of 4a squared is just 2a. So the antiderivative of 2a, since that's just a constant, is 2a times theta. And you're going from 0 to pi, so you just get 2 pi a. And since a is the radius, that's 2 pi r, which is the circumference of the circle. So that gives us, again, some confidence that that formula that we derived is correct. So anyway, that ends pretty much everything you need to know as far as polar calculus is concerned. Now, there's still some good problems that add a little bit of complexity that I want to go over in 1 or 2 more talks, but that'll kind of end up the year. So practice a little bit on this polar area, arc length, and slope, and I'll see you the next time, I hope.